guys, welcome back to another video. This is video 2 of the Math Counts training series presented by Agora Math Circle and of course myself, Mugil Shanmugam. So I highly encourage you guys watch video 1 before this. Video 1 goes over GCF, LCM, magic squares, and introduction to math counts in general. So make sure to go check that out. Link will be in the description below, and you can also find it on our website. Shouldn't be too hard to find. So check that out and then head over to this video and let's get started. So let's get right into it. Session 2, here we come. Right, Session 2 topics. So let's just quickly go over what we're going to even be learning today. Today we will be covering the following: tiles, how many faces are painted, how many triangles with integer lengths, and how many ways to walk. And in this, our subtopics are tiles, common formulas and sample problems, how many faces are painted, explanation and sample problems, how many triangles with integer lengths, basic knowledge and sample problems, and how many ways to walk, basic knowledge and sample problems. Now, you guys might be thinking, that's a lot of basic knowledge and explanation. When I say basic knowledge and explanation, it's simply just going to be like a 1 or 2 sentence overview of the concept or what you need to know. And we'll just go into like a few formulas for each one that will help you understand and use them in different situations. Because you gotta know that everything we're learning here is gonna help you in the math counts exam, but you need to be able to apply these different formulas, or you need to be able, if a concept is giving it to you in any way, you need to be able to answer those questions and succeed on the math counts exam. So that's why we're really gonna dive into those formulas here and the different ways to approach these different problems. So let's get right into it. All right, tiles. Some problems on the math counts exam in general will just involve tiles covering a certain area of the floor. Here are some useful formulas to use in different situations. Now, there is quite a few tile formulas, and don't be too bothered about memorizing tile formulas or any other formulas I'm going to teach in this. Just keep practicing them, practice, and eventually you will become perfect because you will know these formulas. Even if you haven't memorized them, the practice will just ingrain them in your head and you'll be able to apply them in any situation. So just keep practicing using these formulas after we do the sample problem. If you have a diagonal on a rectangular floor of dimensions m by n, the diagonal crosses n tiles. Now, the diagonal crosses capital N tiles. This is an important distinction. When we have a lowercase n, that's generally going to be referring to a dimension I'm using, while the uppercase n is always going to be referring to the number of something, the number of tiles, the number of triangles, the number of ways. It doesn't matter. It's just the number of something. Anyway, so as you can see, I've drawn a blue box here. Not a box, sorry, a rectangle. And you can see that I've drawn a diagonal through it, and I've also labeled m and n for you. So when you're given a situation like this and asked, how many tiles does this diagonal pass through? Use the formula capital N is equal to m plus n minus GCF of mn. So again, if you're confused on how to find the GCF here, I highly recommend you guys go watch the first video of this series so you can learn what GCF is and how we can apply it. But for this, the formula is simply m plus n, so your 2 dimensions, you add them, then subtract the GCF of the 2. Alright, let's move on to the same scenario in a 3D perspective. N is equal to W plus L plus H minus GCF of WL minus GCF of LH minus GCF of HW plus GCF of WLH. Wow, that was a mouthful. But the thing we gotta understand here is it's simply just because we've included another dimension to this rectangular prism we have. Originally, it was just like this length and width. Now we've added the height dimension. That's why we have so many extra dimensions, because now we need to incorporate this height into all of our calculations. So based on the original formula, we were able to find this formula by simply incorporating the height into these calculations. All right, let's move on to the next set of formulas. So tiles, more formulas. I guess that was pretty obvious, but I just stated the obvious. Consider the same diagonal running through the tiles. If you're asked to find the number of 4 corner intersection points crossed by the diagonal, n is equal to the GCF of mn plus 1, if n points count as points that are crossed by the diagonal, or n is equal to the GCF of mn minus 1, if the n points are not included. So as you can see, I have a little grid here, and when they ask how many 4 corner intersection points are crossed, well, basically they're just asking, if you draw a diagonal, how many points is it going to cross? If n points are included, that simply means the point where the diagonal starts and ends, you're including that. If it's not included, you're simply not including that. But these formulas are pretty self-explanatory. You find the GCF and you add 1 if endpoints are included. You find the GCF and you subtract 1 if the GCF is not included. If the endpoints are not included. All right. More formulas continuation. The maximum number of tiles crossed by a diagonal is found by using the following formula. N is equal to m plus n minus 1. So what they're asking in this question and how it differs from previous formulas is before we found how many tiles are actually crossed by a diagonal. This is asking what is the possible maximum tiles that a diagonal, if you drew it into this tile or into this grid, would cross. And the simple formula for this is capital N is equal to m plus n minus 1. Your 2 dimensions, m plus n minus 1. It's pretty simple. Honestly, these problems aren't too much about like complex calculations. They're simply about identifying the right dimensions and identifying the right formula to use. If you can do those things, identify the right dimensions, identify the formula, and plug everything in, you will be golden on the math counts exam. And for square 4, this is just going to be n is equal to 2n minus 1. That probably isn't too much of a shock because m is equal to n in a square. A square has 2 dimensions, n and n, instead of m and n. So 2n minus 1. Right, tiles, sample problem 1. In case you haven't watched my previous video, the normal way we do these sample problems is I'll explain the problem, maybe give a hint or two, and then I'll read the problem, give a hint or two, and then I'm going to ask you guys to pause the video and go ahead and try to solve this problem. Take your best guess. It doesn't have to be correct. It's simply just going to help you. So when you're done solving it, I'll ask you guys to start the video up again, and then I'll go over how you could solve this problem. All right, so let me read the problem. A 24-foot by 72-foot rectangular dance floor is tiled by 1 times 1 foot square tiles. There's a diagonal running from the 2 corners of the dance floor that are opposite to each other. How many tiles does the diagonal pass through? And this is from the 2002 Mathcounts Chapter sprint. Wow, that was before I was in Barn. But yeah, so there you have it, your problem. And remember, check what they're trying to ask you in this problem. Well, in this problem, to me, it seems like they're asking how many tiles does the diagonal pass through? So we learned a formula earlier on in this video on how to do this. So check that out. Rewind the video if you need. Check that formula out. And go ahead and solve this problem. So pause me here and go ahead. Okay, hopefully you paused, you did the problem, and hopefully you're done now, and you're waiting for me to discuss solutions. So let's go right into it. Solution. First, note what the question wants you to find. The question wants you to find the number of tiles that the diagonal passes through. We know that the formula capital N is equal to m plus n minus GCF of n is how we find the number of tiles crossed by a diagonal, n. So in this case, we're simply just applying that formula we learned before. If we want to find how many tiles are crossed by a diagonal, we simply use this formula, m plus n minus GCF of mn. So that's how we figured out what formula to use now. But now that we figured out what formula to use, well, we got to figure out what our m is. What is our n? So we know that we've given the dimensions 24 foot and 72 foot. It doesn't matter which is m and which is n. Just be consistent with your use. By this I mean, if you say m is equal to 24, throughout that problem, your m should be equal to 24. Every single place they ask you to plug in m, it should be 24. If you're consistent with your usage like that, it doesn't matter which variable you assign to which in this context. Alright, so our m is equal to 24, our n is equal to 72, and the GCF of 24 and 72 is 24. Again, if you didn't understand how I got the GCF, I went over that in the session 1 video. Go ahead, check that out, and learn how to do it. Anyway, so now we just plug everything we have into our formula. N is equal to 24 plus 72 minus 24. When we solve that, we get 72. The diagonal passes through the interior of 72 tiles. Pretty simple, just plugging into that formula. Alright, now let's move on to how many faces are painted problems. So these problems are simply going to give you this rectangular prism of dimensions m times n times r. All the outer faces of the prism have been painted. Now if we remove the blocks that make the prism, each one is having the dimensions 1 times 1 times 1, a cube, a small cube basically. If we remove it, they're asking how many faces will be painted. How many of these cubes will have 3 faces painted? How many will have 2 faces painted? And how many will have 1 face painted? For a rectangular prism of dimensions m times n times r with all dimensions greater than or equal to 2, we have a table. on the next slide. So here's our table. If they ask how many of them have 3 faces painted, it's simply going to be 8. If they ask how many have 2 faces painted, it's going to be 4 into m minus 2 plus 4 into n minus 2 plus 4 into r minus 2. For 1 face painted, it's 2 into m minus 2 to n minus 2 plus 2 into m minus 2 r minus 2 plus 2 into n minus 2 r minus 2. And for 0 faces painted, it's m minus 2 into n minus 2 into r minus 2. Total number of small cubes, why, that's just m times n times r. Alright, so let's just quickly go over these formulas and how they work basically. So as you can see, the 3-face, 2-face, and 1-face, 0-face painted formulas, you're simply just plugging in these m, n, and r values you have. Again, as I said, you can use whatever m value you want, just be consistent with your usage of it. Now, when they ask what is the total number of small cubes, well, each of these cubes is 1 times 1 times 1. That means that to find the number of total small cubes, all you have to do is multiply the dimensions you know. And here we have m times n times r, multiply them, and we get the number of small cubes. So again, it's just a set of formulas, but what's going to happen is on the Mathcounts exam, they'll give you a specific premise or a problem, and you need to figure out which table will correspond to that and which one will have the formulas you need. Alright, now this is some more tables, but these are for different situations. For a rectangular prism of dimensions m times n times 1, with m and n greater than or equal to 2. 3 faces painted, well, that's going to be 2 into m minus 2 plus 2 into n minus 2. For the number of blocks with 2 faces painted, that's m minus 2 into n minus 2. For the ones with 1 face painted, it's 0. For the ones with 0 faces painted, it's 0. The total number of small cubes here, that's just m times n times 1. Pretty simple, right? These are just formulas that will come to you with more practice and practice. Don't be too worried about memorizing them. They'll come naturally, so don't worry about that. But these are just some formulas that we're using for the specific scenario. The scenario when you only have the dimensions m and n and your height is just 1. Alright, let's move on to the last table of the section. For a cube with dimensions n times n times n. So we originally have these dimensions m times n times r. But since all the dimensions in a cube are the same, we can simply write it as n times n times n, or n cubed. And n must be greater than or equal to 2. You can see that this is a constraint that just keeps coming over and over. N, or your variable in any case, has to be greater than or equal to 2. For the number of cubes with 3 faces painted, it's simply 8. For 2 faces painted, it's n minus 2 times 2 times 6. For 1 face painted, it's n minus 2 squared times 1 times 6, which is just the same as times 6. And for 0 faces painted, it's n minus 2 cubed, right down there. The total number of small cubes, that's simply n cubed. Again, if I multiply the overall dimensions of my cube or of my prism, I'm getting the total number of small cubes. And I have these formulas that I can apply based on what the question is asking me and what cube, or what prism, I should say, the question is giving me. And you'll see that better when I go into the sample problem. So here we are at our sample problem. Assume you have a rectangular block of dimensions 30 centimeters, 16 centimeters, and 12 centimeters. The constituent cubes of the prism are 1 centimeter cubed in volume. If the outside of the block is painted red, what is the percent of the block that is made of constituent cubes with 2 faces painted red? Round your answer to the nearest tenth. 1994 Mathcounts National Sprint. So this problem's really old, but it'll still serve its purposes. It's good enough for practice today. So for this one, carefully read the problem and tell me which type of rectangular prism format does it fit. And once you figure that out, will now tell me, well, what formula do I have to use? Because each one gives me like 4 formulas: 3 faces, 2 faces, 1 face, 0 face. So which face formula do I need to use for this one? If you figure that out, simply just apply it and you'll be good. Alright, so pause the video here, go ahead, attempt the problem, and restart the video whenever you're ready to begin. Okay guys, hopefully you guys tried it out. Let's move on to the solution for this one. Using our table from the previous slides, we know that the number of cubes with 2 faces painted is 4 times m minus 2 plus 4 into n minus 2 plus 4 into r minus 2. As you can see here, I have 3 different dimensions, m, n, and r, and all of them are greater than 2. That means I can use my first table to find it. And that's how I got this formula, 4 into m minus 2 plus 4 into n minus 2 plus 4 into r minus 2. Because, again, this is the formula you use when you have two faces painted. Right? So now that I got my formula down there, I'm simply going to plug in. Let m equal 30 centimeters, n equals 16 centimeters, and r equals 12 centimeters. Again, it doesn't matter, just be consistent. Using the formula, I just plug in 4 into 30 minus 2 plus 4 into 16 minus 2 plus 4 into 12 minus 2. Now I can simplify using the order of operations, so it's 4 into 28 plus 4 into 14 plus 4 into 10, which is equal to 112 plus 56 plus 40. When I add that all up, I get 208 cubes with two sides painted red. Now, I've seen many students just stop here. They think this is their answer, and they just write that in. But this will get you the problem wrong. You always want to read the problem completely so you can make sure that you know what you're doing is right in any case. Alright, so look at this. It doesn't ask me how many blocks are painted red. It simply asks what is the percent of the entire block that is made of constituent cubes with two faces painted red. So I found the number of constituent cubes. Now I need to find the percent. Well, to do that, that's pretty simple. Should be a simple calculation. I just multiply to find the entire number of small cubes. 30 times 16 times 12, which is 5,760. I've written it down there. And then now I find my percent, which is simply what I have over the total times 100. And when I do all that, I get 3.6111111%. Now, the thing is, the question asks us to round to the 10th. So always follow what the question asks you. So when I round to a 10th, I get 3.6%. And that's my final answer. Okay, let's move on to our third topic for the day. How many triangles with integer length? Assume you have a triangle with integer sides A, B, and C. And A is less than or equal to B, and B is less than or equal to C. So C is your biggest side, B is your second biggest side, and A is probably your smallest side, unless A and B are equal or B and C are equal. But for now, I think it's just easier to visualize it if you think A is the smallest, B is the next, and then C is the biggest. If you know what A is, but you don't know what B and C is, you can form an infinite number of triangles. If you know what B is, then the number of triangles that can be formed is dictated by the formula n is equal to b into b plus 1 over 2. So what this is saying is, usually they're only going to give me one length of this entire triangle. So based on what this length is, I can try to solve and use different formulas to find my answer. And if you know length c, then the number of triangles that can be formed is equal to n is equal to c plus 1 over 2 squared. The whole thing is squared. Now, after you square it, you want to move it to the nearest integer. And usually this will be denoted with a set of a big less than symbol and a big greater than symbol on either side of it. This simply means round. Well, not exactly round, just move to the nearest integer. And yeah, so make sure to do that for this C equation only. But as you can see, all three of these equations are very useful because they're allowing us to solve this problem if we're given only one side. But sometimes we won't be even given these sides, we'll be given other information. So on the next slide and the slide after that, we'll figure out how to deal with it if we're given perimeter or if we're given like the sum of two legs. Okay, use this formula if you know n is equal to the sum of two legs. So let's just say that they give you a plus b is equal to 25. So you can't really find what a and b is. It's not enough information, but you know what n is. Lowercase letter n. N is equal to 25. So simply plug into this formula to find the number of triangles you can create. Again, here in this formula, what you're doing is you're doing n divided by 2. Then you might see this weird bracket-like symbol. This does not mean brackets. If it doesn't have the top part of the bracket, simply the bottom part, like an L on either side, this means you have to move it to the nearest integer. So if it's 7.99, I move it to 8. If it's 7.3, I'll move it to 7, and so on. And I square this. So that's how I find the number of possible triangles if I'm given this n is equal to the sum of two legs. Finding the number of triangles given perimeter. I have a table on the next slide where we have a given perimeter and we can find the number of non-congruent, so non-similar triangles with integer lengths possible. Q is equal to P over 2 if P is even, and Q is equal to P plus 3 over 2 if P is odd. k is a positive integer. So k and q might be a little confusing now. It'll make more sense when I show you the table. You can see how they're used. But for now, just know if your perimeter is even, you can find q by doing p over 2. If your perimeter is odd, just do p plus 3 over 2. Alright, so here's our table. Now, as you can see, I've written a bunch of q values on the right side, and then on the left side, I have a bunch of n values. So this n value is what we're trying to find at the end. So at this point, we're supposed to have figured out a q value, and then we find out which distribution fits that q value. For example, let's just say you're given q is equal to 7. Well, 7 fits the distribution 6k plus 1. You know why? Because when I plug in 1 for k, 6 times 1 is 6, plus 1 is 7. So that's how I get this q is equal to 7 fits this distribution, q is equal to 6k plus 1. And similarly, as you can see, I have q is equal to 6k, q is equal to 6k plus 1, q is equal to 6k plus 2, q is equal to 6k plus 3, plus 4, plus 5, and so on. It goes up to plus 5. Now, again, k must be a positive integer or 0. Now, here on the other side, we have these n values. So once you've figured out what distribution q fits, you plug it into this formula, your q value. So if it was q is equal to 6k, I plug it into the formula q squared over 12. If it's q is equal to 6k plus 1, well, I plug into the formula q squared minus 1 over 12. And so on. So basically, you figure out which distribution matches, and you match it in the table. So I would advise you to keep this table handy. Over time, it will just become second nature, it'll become memory. But for now, just try to use the table and find your answers. Right. Final relationship to use with triangles, if a plus b plus c is equal to perimeter. That's pretty obvious, right? If you add up all the sides, you get the perimeter. Then c is less than the perimeter divided by 2. So what this is saying is the biggest side of this triangle is going to be less than half of the perimeter. It's a simple relationship. You might be wondering where this comes into use. Sometimes you can check your answers using this. You can check that your C is correct. And sometimes they'll maybe ask you, is this a possible triangle? Well, you can check and figure out that, oh, well, my perimeter divided by 2 is not as big as my C, so it can't be a real triangle, or so on. Okay, we have a SEM problem here. How many different triangles can be formed having a perimeter of 7 units if each side must have integer lengths? Again, this is from Mathcounts. Okay, so this problem is based on the perimeter values that we saw before, the perimeter table. You have your perimeter, you have to find your q value, you need to find your k value, you need to find which distribution fits your q, and then you need to plug it into the n formula, the capital letter N formula. So go ahead, give it a go, pause me, and restart the video when you're ready to move on. Alright, hopefully you guys took a pause, did the problem, took a break if you needed it, so let's get back into it. To solve this problem, we need to use the formula table when we're given the perimeter. Our perimeter is 7, so q is equal to p plus 3 over 2. How do we know this? Well, if the perimeter is odd, we use p plus 3 over 2 is equal to q. 7 is odd. That's pretty obvious. So we can use this formula, and when we do it, we get 10 over 2, which is equal to 5. So our q is 5. We've calculated that. So now we need to find which distribution fits my q. Well, I'm going to scroll back here to my table. The only distribution that fits q, in my opinion, from the table, is that this last one. Q is equal to 6k plus 5. Because if you think about it, my q is 5, right? So 5 is equal to 6k plus 5. That makes sense because k can be 0. Remember, k must be a positive or 0 integer. Integers only. So that's the only one that fits. So I can conclude that it's based on the distribution q is equal to 6k plus 5. That means that it corresponds to the formula n is equal to q squared minus 1 over 12. Alright, so that gives me a lot of help now. Now I know what formula to plug in to find the number of possible triangles I can find. So I scroll back real quick to my problem, and I find that I can just plug in my q. Q squared minus 1 is 25 minus 1 over 12, which is 24 over 12. I've written it out here, which is equal to 2. This means we can only form 2 different triangles with a given perimeter, provided that the lengths must be integer. Now, if the lengths could be decimals, we could probably find infinite triangles, many triangles, but this is only when the lengths are integers. Okay, so let's move on to the last topic for today, how many ways to walk. All right, in an m times n grid, we can find the number of ways to walk from one corner of the grid to the other using the following formula. So when I say one corner of the grid to the other, well, like let's just say that this, if you see my camera from one corner to the other, that would be a sample grid if you had grid boxes on it. And basically we're trying to find how many ways can you walk from the top of my camera, the top corner of my camera, to the bottom corner of my camera. That's what we're trying to find using this. Now you see some combination notation here, m plus n, choose n, and m plus n, choose m. So this is combinations of permutations. We will go in depth into them in a later video. For now, just know the basics, and I've given factorial formulas, so you can just plug into the factorial formula instead of using the permutations and combinations for now. And we'll go over those in a later video, as they are also required topics for math counts. But for now, just know that capital N is equal to m plus n factorial over m factorial times n factorial. M factorial times n factorial. Okay. So what I mean by that is you add your m and your n. So you add your dimensions of that grid, you find the factorial of that on the numerator. Factorial simply means multiplying a number by all the numbers underneath it, or that are less than it, up to 1. So an example is 6 factorial. That's 6 times 5 times 4 times 3 times 2 times 1. 3 factorial. 3 times 2 times 1. So on. That should be pretty easy to understand as long as you understand the notation. And on the denominator, you have m factorial times n factorial. Right. So now we're going to go over product and sum rule pretty briefly. This is a very broad overview. If you look at some of the probability videos we have on our channel, you can go more in depth into these rules and how they work. But I'm just giving you a broad overview here, but this is a very vital concept. It'll come back in biology, in chemistry, physics. This is very important. When a task consists of k separate parts, the first way can be done in n1 ways, the second task can be done in n2 ways, and so on till the last part can be done in nk ways. The total number of possible results for completing a task can be found by n1 times n2 times n3 times n4 times n5. So basically this is just telling us we have these different parts of the same task, and we need them both to be completed together. It's an and situation. We can multiply. But if we have an or situation, or such as when an event E1 can be done in N1 ways, an event E2 can be done in N2 ways, an event EK can happen in NK ways, and if each event occurs independent of each other, the total ways to get the job done consisting of all events is N1 plus N2 plus NK. So when I have the dots there, I simply mean so on. So this is how you would do it if you have two mutually exclusive events that are independent of each other and you're trying to find what is the probability of them happening. So yeah, let's move on. More formulas. So the number of ways a bug can crawl across the floor of a line, the lines of a frame from one corner to the other diagonally opposite corner of a rectangular frame of dimensions m times n times r, so that means it's three-dimensional, right? Is capital N is equal to s factorial over m factorial, n factorial, r factorial. And s is equal to m plus n plus r. So again, this is just the number of ways that we can calculate for a bug to crawl across the lines of frame. So basically on the edges, right, or on the grid lines to get to that final point. Bug crawling in grid lines. So this is what I'm talking about, the bug that crawls on the grid lines. How many ways does it have to get to that final point? The same situation, but this time the bug crawls across the grid lines of the surface. You get the formula. Capital N is equal to 2 times n plus r, choose 1, n plus r, choose n plus r, choose r, minus 2 times n plus n, choose n, plus n plus r, choose r, plus r plus m, choose m. So this is all combinations. Basically, it's referring to the possible ways that I could choose the bottom value from the set of the top values. So for example, n plus r, choose r, the possible ways that I can choose this r value from the total of the values provided to me by n plus r. And we will go into this more depth in future videos. For now, just know the formula, and you should be able to apply it based on that. Right. And for a cubic solid instead of a rectangular solid, again, so we've seen this a lot today, where we have this rectangular solid of dimensions m times n times r, but then when it becomes a cube, you can just change everything to the same dimension. So in this case, we've elected for m. So it's 6 times 3m, choose m, minus 2m, choose m. So that's simply how we can find the number of ways the bug can walk across the grid lines to the corner in a cube. crawling forward and back. This is the last crawling problem, so just hang in there. For an ant crawling the length of 2n and coming back where it started on a piece of grid paper, when the length of the small squares of the grid is 1, the number of different paths it can crawl will be n is equal to 2n choose n minus 2n choose n. So this is if the bug is going like this up to the corner and it's coming back down along the same path. How many ways can it go to achieve this task? Well, that's how we're going to figure this out using this formula of combinations. Again, if you want to know how exactly combinations work, I'd encourage you to check out the other videos on our channel to learn the formulas. This is just a broad overview of the topic and how it applies to our formulas. We aren't really going into like the very essence of combinations, since that's for a later video, but check it out on our channel if you want a little more help with it. Alright, here's a sample problem, so let me read it real quick. You want to get from point A to point B, but certain paths are blocked. You are currently attempting to figure out all the possible paths available to you. How many possible paths are there to get you to your destination? Right, so we've given you these, I've given you a grid at the bottom. You can see point A, point B, and your grid, 3x3 grid. So try to use a formula that we learned in this how many ways to walk, apply it, and go ahead and do it. Pause the video and play it again when you're ready to start. Okay, hopefully you took a moment to do that. Let's go into the solution. For this problem, we need to use the formula m plus n factorial over m factorial times n factorial to find the number of ways we can use to go from point A to point B. So again, the number of ways we can go from one point to the other when they're diagonally opposite, we have to use this formula m plus n factorial over m factorial times n factorial. Now, our m is equal to 3, our n is equal to 3. Sometimes this confuses people. Remember, we're given an m times n grid. Our m, well, let's just say our m here is our width. I count 1 grid, 2 grid, 3 grid as my width. So that's 3. And my n is also going to be my length. So my n is my length. So that's 1 grid, 2 grid, 3 grid. So I can find 3 grids there. So it's a 3 by 3 grid. That means both my m and my n are 3. So I can simply plug this into the formula. I'll get 3 plus 3 factorial, which is 6 factorial, times, 6 factorial over 3 factorial times 3 factorial. Now I can simplify this. So 6 factorial is 6 times 5 times 4 times 3 times 2 times 1 over 3 factorial, 3 times 2 times 1 times 3 factorial, which is 3 times 2 times 1. Now we can do a little quick cancellation here. I see a 3, 2, and a 1 multiplied on the top. I see a 3, 2, and a 1 being multiplied on the bottom. I'll do a quick cancellation. I got rid of those, and I'm left with 6 times 5 times 4 over 3 times 2 times 1, which is 120 over 6 simplifies to 20. Pretty simple. So there are 20 different paths you can take. Now, some people will get confused by this extra additional information I threw into this question. I said certain paths are blocked. Now, some people get overcomplicate this problem. They're like, well, if some of the paths are blocked, what should I subtract from this 20? Just simply look at what the question asks you to find. The question asks how many possible paths. It doesn't ask about which path can I use. It simply asks what are the possible paths there are. Possible paths, they can still include blocked paths because that's still a possible path you can take. You just have to turn back. So that's how we'd figure this out, ignoring the extra information. When we get there, 20 different paths you can take. Alright guys, thank you so much for watching. Please like the video if you enjoyed it, and smash the subscribe button if you enjoyed our channel and you want to learn more about math. Any topic you want, it's on our channel. Go check it out. Leave a comment with any questions you have, and make sure to click the bell to get notified when we drop a new video. And if you also have any questions, you can also email info@agoramathcircle.org. Thank you so much for watching, and have a nice day. Bye.
Don't forget to subscribe and like. If you have any questions, you can email info@agoramathcircle.org or comment below and we'll reply back. Maybe. And if you want to see practice things or anything about us, you can visit our website, which is basically the end of the email but without the info and the end. So bye!